Let's revise time domain. In time domain, we will be majorly talking about unit step responses. For first order unit step responses, for first order system and second order system. Okay, so we'll be majorly looking into unit step responses. Then we will look into settling time. We will, depending upon the error band, we'll see what error band means. We'll see rise time, we'll see delay time. Then for second order, we will see the time when it crosses, when it is crossing 0. We'll say peak rise time. Then second, the dip of it, minimum we will see. We will talk about time period. We'll talk about different systems like underdamped, undamped, critically damped, and overdamped. And in that way, we'll proceed the lecture. So let's get started and see first order system first. But before that, just a brief intro of pole zero format. So pole zero format is majorly used in root locus. Okay, pole zero format is majorly used in root locus. Time constant format I'll be using for Nyquist and Bode. Okay, for this particular chapter, we shall see what we do. So first thing to take care is the first order system, closed loop first order system में forward gain would be 1 upon s tau. In this case, your c of t, your response will be a into 1 minus e की power minus t upon tau, where tau is nothing but rc. So your response will be nothing but this way. Okay, we shall see that ahead. Okay, now we shall see different timings here, but before that, let's discuss shortly about low pass filter, RC low pass filter. In RC low pass filter, tau becomes RC, and your forward gain becomes 1 upon src, 1 upon s tau, right? So here tau is replaced by rc. You get something, and then you can proceed your calculation and your analysis depending upon these values. Fine, now let's get started with the first order system. So this is going to be the response. Firstly, we will see about rise time. So rise time is time taken to rise between 10% to 90%. Okay, the time here is nothing but rise time, and rise time is nothing but 2.2 tau. Now tau is inverse of bandwidth, so 2.2 upon bandwidth. In case you need to make it into frequency, bandwidth is given in frequency, it becomes 2.2 upon 2 pi f. That comes out to be 0.35 f in hertz. Okay, bandwidth is nothing but in radians per second, but if it is in hertz, so it will be either 2.2 tau or 2.2 upon bandwidth in radians, or 0.35 upon frequency in hertz. That is the story of rise time. Then we'll look into delay time. So delay time is nothing but 0.693 into tau. Now settling time. So settling time you can give for certain range. Settling time can be given for certain error band. More the error band, less will be the settling time. Fine. So settling time for 2% is 4 tau, for 5% is 3 tau, and this will be constant throughout. For every system, it is going to be 4 tau for 5%, for 2%, and 3 tau for 5%, except critically damped system. For critically damped system, 2% error band, it will be 6 tau, and 5% error band, it is going to be 3 tau. Okay, so we need to take care. For critically damped system, 2% is 6 tau and 3% is 3 tau. For rest all systems, 2% is 4 tau and 3% error band is nothing but 2 tau. Fine. So this is all the discussion about first order system. Output response is a into 1 minus e की power minus t by tau. Rise time is nothing but 2.2 tau. Delay time is 0.693 tau. Settling time for 2% error band is 4 tau and 5% error band is 3 tau. Now moving to second order system. Second order system standard equation would be omega n square upon s into s plus 2 zeta omega n. This is nothing but the forward gain. Now to remember different zetas, we shall keep one diagram into consideration, one circle. On axis you get zeta is equals to 0, that is undamped, on y-axis, so which means that roots are complex. On x-axis you get zeta equals to 1, which means a real negative root repeating. Then between 0 to 1 you get zeta less than 1, so poles would be lying somewhere on the circle, and that is for underdamped. And on x-axis, left and right side of zeta equals to 1, you will get zeta greater than 1, which is overdamped. Okay, so always remember that whatever comes right side of the circle, that is unstable, and whatever comes to the left of the, so the poles which lies on the left of s plane, basically those are stable, the systems are stable. The rest of the systems which lies on the right side are is unstable system. Okay, now let's look at the responses. So undamped meaning no damping, meaning proper sinusoidal kind of response. But for critically damped, overdamped and underdamped. So for underdamped, it would be a decreasing function, or decreasing sinusoidal. For critically damped and overdamped will have similar responses, but the critically damped is much faster. It would reach steady state value much faster, and overdamped is very much sluggish. Okay, overdamped is very much sluggish. Now before moving ahead, let's quickly look into some of the important terms. So what is omega n? Omega n is natural frequency of oscillation, omega t is damped frequency, zeta is damping ratio, and zeta omega n is nothing but damping factor. Okay, omega t is damped frequency, zeta is nothing but damping ratio, zeta omega n is nothing but damping factor. Okay, fine. Now let's quickly so again we shall remember that the standard second order system is nothing but omega square upon s plus 2 zeta omega n. Okay, this is open loop gain. If you want a closed loop gain, you will get omega n square upon s square plus 2 zeta omega n plus omega n square. Okay, so here we need two things to get any of the results, that is zeta and omega n, damping ratio and frequency of oscillation. Fine. So as I've already told, for undamped frequency, your root will be minus zeta omega n plus or minus j omega n root of 1 minus zeta square. Okay, and the some important formulas are bandwidth is nothing, bandwidth is nothing but so tau is nothing but 1 upon zeta omega n, and settling time is nothing but, as I already discussed, 2% error band, it will be 4 tau, and for 5% is 3 tau. And one more most important thing is zeta is nothing but cos inverse phi. Most important thing, zeta is cos inverse phi. This will be majorly used, this will be given in questions, so you need to understand that phi meaning they have given information about zeta, or in percentage MP also you can use that, e की power minus zeta pi upon root of 1 minus zeta square, that comes out to be nothing but phi. Okay, now see, this is nothing but, yes, that comes out to be nothing but phi. So from there you can write that. Okay, cool enough. So see, this value is nothing but omega n root of 1 minus zeta square, and since the y-axis value is that, Yes, you can write here as e की power minus y by x, right? Y by x, so x by y. Okay, so you can write pi upon tan phi. Okay, so from phi you can also do this kind of manipulation in percent MP. We shall see what is percent MP, but before that let's look at all the responses for underdamped, overdamped, critically damped, undamped, etc. So for underdamped, it is C of t is equals to 1 into a into 1 minus e की power minus zeta omega nt upon root of 1 minus zeta square sin omega dt plus phi. For undamped, it is nothing but a into 1 minus e की power. So for undamped, zeta is nothing but 0. Okay, so it is 1 minus e की power 0 omega nt. So there is no e की power 0, that comes out to be 1. So the expression comes out to be a into 1 minus cos omega nt, because here for undamped omega n is equals to omega d. Okay, and one thing to notice here, maximum peak overshoot can be a. So maximum magnitude of undamped signal is nothing but 2a. Fine. And another important thing I want you to notice, there is no settling time as such. It will never settle. So settling time is nothing but infinity. Settling time is nothing but infinity. Now critically damped and overdamped. So the responses are almost the same, but there is a difference. So critically damped meaning zeta is equals to 1 and a real negative repeating roots. As I already told, it is very fast, so shortest possible time it takes to reach the steady state. Tau is equals to 1 upon omega n. Tau is nothing but 1 upon omega n since zeta is 1. Settling time in first 2 minutes only I told that settling time in critically damped signals, critically damped system would be 6 tau. Okay, poles lie on omega n circle. Its response is nothing but a into 1 minus e की power minus omega n t into 1 plus omega n t. Okay, now coming to overdamped system will have real poles, so naturally you will get some response in e की power minus mt plus e की power plus mt, such way. That's okay, but it is this sluggish, it's just sluggish, and it will take the longest time. It will take the longest time to settle down. Now most important thing is tau here. Tau in this case is going to be nothing but 1 upon roots mod of roots, but 1 upon mod of roots, but here since both the roots are real, you will be using dominant pool concept and you will be taking the first root. Okay, now there is a number of cycle concept, but let's see this in a short while. Okay, now let's quickly discuss some of the formulas which are related to second order underdamped system. Okay, first step input, of course. So for step input underdamped system, the points which crosses the steady state values is nothing but n pi minus phi upon omega d. For n is equals to 1, we call it as rise time, that comes out to be pi minus phi upon omega d. Okay, then peak values are given by 2k minus 1 pi upon omega d, and dips are given by 2k pi upon omega d. Okay, so the first peak overshoot would occur at the time of 2k minus 1 pi upon omega t, and first undershoot would be 2k pi upon omega d. Okay, and the maximum value of overshoot from the steady state value is nothing but a e की power minus 2k minus 1 pi upon root zeta pi upon root of 1 minus zeta square. Okay, let me again say, it's nothing but a into e की power minus zeta pi root of 1 minus zeta square, but here you need to add the value 2k minus 1. This is for any overshoot, but for first overshoot the k is going to be nothing but 1. Okay, So the maximum value becomes what? A plus this value. And similarly for undershoot, it is what? A minus A into, correct, A into e की power 2k, okay, 2k zeta pi upon root of 1 minus zeta square. That is nothing but undershoot. Okay, this is nothing but undershoot. Yeah, so basically if only percentage maximum overshoot is asked, you will do a e की power minus zeta pi upon root of 1 minus zeta square into 100. What do you mean by percentage overshoot? It is t peak, c t of peak minus c t of infinity upon c t of infinity. Okay, one of the shortcuts here to remember is if percentage mp is given, you will just divide it by 100 and you'll call it p, and zeta is nothing but root of ln p whole square upon pi square plus ln p whole square. It is as simple as that. Okay, so that is it. Now moving to and one more thing, whenever peak overshoot is given 16%, this is frequently common question, zeta is nothing but 0.5. Now let's move to this problem wherein g of s is given and it is asked to find out, calculate k if both the poles are in the same location. What does this mean? This is possible only in critically damped. Critically damped meaning zeta is equals to 1. That is the hint point. Now find it out. Simple only. Has minimum settling time with no overshoot. Meaning what? Again, critically damped. Zeta is 1. Find out the value. Okay, what's there? Right? So with this we can conclude this particular chapter. Next we will see the stability. Thank you.